Let's talk about the Hamiltonian in quantum mechanics today. What is the Hamiltonian? The Hamiltonian is an operator when applied to the quantum state, let's say a wave function of a particle or a system. It tells us what the possible values of the total energy of the system is/r. It is denoted with a hat on top of it, and it is equal to the kinetic energy operator plus the total potential energy operator. I realize that I should have said this earlier, but in quantum mechanics, all measurable quantities, for example, in this case, the total kinetic energy of a particle or a system is represented in terms of operators. For example, over here, since we're discussing kinetic energy, the kinetic energy of a particle is an operator calculated by taking the dot product of the momentum with itself, all divided by 2m. But in classical mechanics, we remember that the total kinetic energy would be calculated using T equals p squared all over 2m. So that this is a common difference in between classical mechanics and in quantum mechanics. But if we carry out this thing over here, we will get a very interesting value. Well, we need to know what the p hat operator, which is the momentum operator, is first. So the momentum operator in quantum mechanics, p hat, is negative IH bar, the first derivative with respect to x. So that tells us that t hat is basically and in general, the potential energy of any particle is just a function of position. It's generally not a function of time, and we disregard those examples when studying Intro to Quantum Mechanics. So this is a function of position. All right. So now that we're done with kinetic energy and potential energy as represented with the Hamiltonian, let's recall the Schrodinger equation and how it looks like. The Schrodinger equation basically says that IH bar, the partial with respect to t of psi x comma t, where psi x comma t is your total wave function, is equal to the negative h bar squared all over 2m. The second partial with respect to x of psi x comma t plus vx psi x comma t. Now notice that this entire term basically looks like your t hat, which is your total kinetic energy, and v basically looks like your total potential energy. So when you add these things up, all of the term in the right hand side associated with psi x comma t becomes your Hamiltonian. So we can rewrite our Schrodinger equation as being IH bar ddt psi x comma t as being equal to your Hamiltonian applied to psi x comma t. And this is your updated Schrodinger equation written in terms of the Hamiltonian. So we see that the Hamiltonian in the Schrodinger equation gives us the time evolution of our system. So applying the Hamiltonian on your wave function would give the total energy in terms of the eigenvalues of your wave function being eigenfunctions. Now let's move on to finding the expectation value of your Hamiltonian. Since we did expectation values for quantities such as x, p, x squared, and p squared. So let's find the expectation value of your Hamiltonian of h, meaning we're trying to find out what the expectation value of h is. So let's begin by writing what the expectation value is in terms of definition. This is basically taking the integral of psi star and sandwiching your Hamiltonian operator in between psi star and psi, taken as integrated over dx. Now recall that your psi, I should be writing psi over here like this. So psi is basically a linear combination of all the possible stationary states, right? So we can compute that back in over here, and we get that this is basically the summation of C n star psi n, the Hamiltonian, applied to the summation of C m, I should be writing this down as m, C n psi n dx. Yeah, so these are m's, and the one in this summation are n's. N's and m's are dummy indices over here that we will get rid of later on. Now notice that these c's are in no way functions of x, so we can pull them outside, pull these summations outside, and we have that this is basically C m star C n, and inside the integral we have psi m, the Hamiltonian, applied to psi n integrated as a function of x. Recall that we said that m and n are dummy indices, so getting rid of the dummy indices, we can write this down as the summation of all c sub n squares, right? And inside the integral we still have our psi m, right? I should write this down as a star. I forgot to write that down. So we have psi m and the Hamiltonian applied to psi n, right? And notice that this term over here, when we discussed the Hamiltonian being applied to psi n, would just basically give us E sub n psi n, the total energy of psi n, right? So we can write this down as E sub n psi n dx, right? And then again, what we can do is we can pull out the E sub n outside, and then we have the integral of psi m star psi n dx. All right, and recall that this has the formation of the conical delta function. So recalling that, we can write this entire thing down as the summation of c sub n squared E sub n times 1, because this entire term is 1. All right, and so basically we have that the mean value of h, or the expectation value of the Hamiltonian, is basically the summation of c sub n squared times E sub n. And yep, that is all.